Hello, my name is Michael Nickapuk and I'm President and CEO of Force Power Energy. And this is my assistant, Larry Tabb.
Hello. Michael, I'd like to
Yes.
ask you a couple of questions in regards to the company and the product you're developing.
Sure.
First question would be, what made you go down the road of natural gas compression?
Well, I saw that the government was promoting a lot of incentives for this fuel that we had for quite some time, but I know at one point it went dead. It is now being reintroduced, and I was interested in getting involved in energy. And I had purchased some systems overseas, CNG compressors, and different types. And none of them worked when they arrived. They were leaking gas, and there was many other problems I tried to fix. I fixed most of them, but then I noticed the system wore out prematurely. There was nothing good about its design. I worked with the manufacturer, and I saw it completely needed to be re-engineered and redeveloped in order to work properly. At least that was my take on it.
So since you decided that it needed a ground-up development on here, how long did that take?
Well, it took me about 2 years. I designed it on computer. Nearly 100% of the design was all done in a CAD system, which I had done. And I also, because of my manufacturing experience, had sent out requests for quotations on various components, some of which I wasn't intending on manufacturing or having manufactured on the outside. So 2 years development on CAD, receiving quotations, and then about another 6 months I spent with the manufacturer that I chose to make most of the critical components. About another 6 months conveying all the data and criteria and those drawings, explaining every detail, and getting quotations as well for that. So I guess probably 2.5 years before actually any component was manufactured on that design.
So you had to have quite a few components made from around the world, manufacturers. Were there any issues with it when you received the finished product?
Yes, there was actually quite a few issues. Number one, there was some cost issues, but it wasn't as important because in production the cost would change. But because this was one of something or 2 or 10 of something, it was not an issue at that point. But what was an issue more than anything was the quality. There was so much detail in these components. Some of the geometry was very extensive, and they had a lot of errors, so there was quality issues, and there was lead time issues. In other words, the delivery of what was promised was 200–300% later than the actual proposed date that it was supposed to be delivered.
How did you remedy the quality issues when you were working with manufacturers around the world?
Well, depending on the issue and who the manufacturer was, some components I redesigned so they could actually understand or maybe be able to make the part right this time, the second time around. So we lost time in that. Other issues with certain features of machining that were incorrect. I had a piece of equipment and had bought tooling and was able to fix a lot of the errors that were machined into the components. And some of the parts because of the lead time, the cost, the complexity, I manufactured it myself, and I just spent time night and day, 7 days a week sometimes, manufacturing those parts myself. And then maybe one other issue, or resolution to an issue of quality, I had sourced to a different manufacturer, and that was with no prevail. I mean, it was bad. So I made those as well.
You know, it's my understanding that there were some pretty complex materials used in this machine. Was it difficult to get those materials, and was it really difficult for the companies that were doing the machining to do those operations?
Well, it's funny you ask about these materials, because I guess a little bit of my background that I didn't talk about was I have a lot of experience with metal fatigue and high-tech alloys, which in my prior history, I was an inventor, and I developed new tools and technologies for mass producing them. And I designed and built cycle fatigue testing machines to test many materials, heat treating processes, and so forth. So that was another reason why I chose this, to be something I might be good at, because it looked to me that the machines were wearing out prematurely because of poor choices of material besides design issues. And there's high-tech coatings and so forth. But yes, there was a lot of problems. A lot of the companies didn't even hear of the materials that I chose, and/or the heat treating processes that I prescribed for these materials and coatings. And the consequence was that they didn't make the parts right, or they weren't the right hardness, or the right surface treatments, or treatments in general. So that kind of ate up a lot of time, because these components needed to be sent to the lab in order to be analyzed, and that just was out of the question in the terms of time frame, in the terms of cost. It was cheaper actually to remake the part. But yeah, most of the manufacturers didn't even know what I was talking about, and it was on the drawings. And I don't think a lot of the processes were performed correctly, no matter where they were sourced from.
So after all of the components, when they finally arrived and the issues were taken care of with the manufacturing and the heat treating and the materials, and you finally assembled the machine, were there any major problems that you encountered?
Well, when I first fired it up, yeah, there was a multitude of problems. A very complicated piece of equipment, and I actually anticipated problems with, say, the valves. I had completed a design and had these components manufactured, and I knew that it was going to be an evolution there. So that was probably one of my bigger challenges, was to design a valving system that would perform over and above what the industry has. And the other issue, well, first of all, the machine worked, so let's put it there. It fired up and it worked. And
Well, that's a good thing.
yeah, no, yeah, it was a great feeling. I mean, imagine, I mean, we're going on like almost, getting near 3 years before I actually heard it run. And, I've been on it 24/7.
And 2 years of that was designing it on a computer.
Right.
We don't know how it's gonna sound or run on a computer.
Yeah. Well, one of the manufacturers does a lot of engineering and work with Airbus. They're no overseas company. Not Airbus, but the manufacturer. Airbus is a European, like Boeing in the United States. And they said there's no way the machine could work. Because it's really unusual, actually, how I engineered and designed, developed all these components and they said there would be no way to assemble it, and yeah, it's assembled, and it runs and it works.
You had touched at the beginning of our conversation in regards to you purchasing a couple of CNG compressors, and you found issues with them. What does the industry have issue-wise with the technology that's out there today?
Well, that's a good question, because I was shocked at how many issues there were, at least with the systems that I bought. Also, later on, I learned that the gas companies and the customers that have CNG powered vehicles have nothing but problems with CNG filling stations on a commercial level, and also on a home level, you know, where guys are buying very inexpensive, basically compressors that are not performing, underperforming, or require lots of maintenance and a lot of expertise to fix these systems. Yeah, that's a big question to answer, and when I really dug in deep, premature wear in stage 4. These are multi-stage compression machines because they're very high pressure pumps, and the best pumps that go under high pressure are normally reciprocating type piston type machines, multi-staging. You have to do multi-staging for a lot of reasons, and most of the industry does at least 3 stages of compression to get to 3600 psi. I developed a 4-stage system, which there are many 4-stage systems out there. But stage 4, piston rings wearing out, rods, sulfur hydride attacking materials, acids in the gas, liquids, non-compressibles in the gas, destroying, we call it slugging in the compressor world, where it can't compress a liquid, or sometimes the gas company spikes the gas because its BTU output is too low, and they spike it and they put in pentane, butane, propane, which are gases that compress, literally turn into liquids in stage 1, and it's got 2 or 3 more stages to go before it comes out. And so that's a big problem, and that's destroying equipment, and that was something I really had to dig into to solve and make a better machine than what's currently available.
Those sound like pretty complicated issues. Were you able to take and address them in your machine?
Well, they were extremely complicated, and I didn't even bring up the multitude of other issues, serious issues with valves, valving mechanisms, valve guards, which are valve stops and so forth, and valve springs. I don't mind touching on some of those points. First of all, at the frequencies that my machine, my development is running at, it's as much as 4 times higher frequencies than any machine on the market. And in reciprocating equipment, when you double the frequency or double the RPM, you quadruple the death and destruction of the components. And there's a lot of reasons why I chose to go to a high frequency. It would have been a lot easier for me to slow my machine down like the industry, but there's a lot of unique things in the way I approach this, and one of which, I have 7 pistons. There's 10 pistons in there. There's 4 stages. 7 pistons are employed in stage 1. So what I'm doing is every 36 degrees, there's compression taking place on the next piston in stage 1. So every 36 degrees, 7 times. So by doing this, and some companies are doing it twice, they do it 7 times. By doing this so many times, what I'm doing is, as the gas is moving through the pipe, there's what we call slippage, and the gas backs up because of the pulse effect of compression. So because I'm advancing that gas, and it does slip back a little bit, but not as far as others. And I'm advancing it every 36 degrees 7 times. So I end up with less pulses, even though there's literally more, but the shock load is diffused because it's divided by 7 times. So the result is I get at very low gas pressures, which, by the way, in the United States, a common gas pressure is 7 inches of water column, or about 1/4 psi. That's pretty standard. And that's literally no driving force to feed stage 1 in a multi-stage compression machine. And so because of that, I was able to run at a much higher RPM. And that also, because there's a delay, even though the gas is light, it has mass. And when it starts to back up, it's moving so fast, by the time that mass goes backwards, it keeps ratcheting forward. End up with better output, basically. And then I had to deal with the consequences of the death and destruction, as I described earlier, that happens to the components of the machine. But because of my vast experience in metal fatigue, cycle fatigue testing, coatings, inside radii, outside radii, how they adversely affect the performance of a component in combination with knowing what materials and heat treating processes to be used. I was able to develop a machine that could withstand these very high frequencies. And the valve springs could never withstand, no matter what spring configuration that I designed, no matter what material I chose for the springs, they would crumble. They literally, sometimes I thought I didn't put them in, they were just gone. It disintegrated in the machine, it just digested it. And so what I had to do was I eliminated using springs. There's no springs in my compression system whatsoever. And a lot of which is very proprietary. So I won't disclose those details, but you know, if you sign a non-disclosure agreement, well, you'll be my assistant. You don't have to worry. But you guys out there, you know, so.
And how are the new valves, the design, the evolution of these valves, how are they performing in the machine now that you've eliminated the springs and you had a new configuration? How are they performing in the machine? Are they where you thought they would be? Did they exceed your expectations?
Well, I expected that I would develop a valve that wouldn't fail. And what I was surprised about how difficult that was. But I accomplished it, and I'm not incorporating any plastic materials. There's no plastic compositions in my machine. You know, there's nothing wrong with it. Some companies use that. But there's nothing like a steel, a metallic component, highly alloyed metallic component. But it was about the design. The design was more important than the materials that I used. The materials enhanced it. Yeah, I was surprised how difficult that was to achieve, but I achieved it to such a level that whereas I could run the machine 1,000 hours before, and these valves would be all worn out, and the valve systems behind it, valve seats and guards and so forth, to now where there is no wear. There's no wear whatsoever, virtually none, especially when you understand machining and understand surface finishes and how they play a critical role in longevity and equipment. But that's not the main ingredient here. But everything counts when you're trying to, you know, let's face it, I'm competing with companies that put rockets into space. I mean, these are very wealthy and very intelligent people that work at these companies. And there's a lot of them, and there was only me.
And developing good products. And you are just you, and you developed what I consider, a little bit biased sitting here, but a phenomenal product.
Well, thank you. It's such a good feeling, you know, after literally 5 years of development to be, you know, at a point in which, you know, just the results are very impressive. And the industry's soon gonna learn about that.
Yeah, that's definitely very interesting how you tackle the valve issues, and two other very intriguing components, sub-components on this machine are the cooling system and the lubrication system. Can you touch on those briefly?
Yeah, with my experience in metal fatigue, and cycle fatigue, I knew right from the start that this machine needed to be liquid cooled, basically antifreezing water. That's not unique that it's liquid cooled, but what's unique is the size of this machine and going with liquid cooling and knowing that this is a key component to a successful product that's going to have high longevity. The piston rings, the valving system, other components, maintaining temperature, seals. Seals are very temperamental to temperature, even though these great materials like Viton withstand these very high temperatures. You lower the temperature or maintain a constant temperature that's uniform around the seal, and you're going to have a very predictable seal life, a longer seal life, and maybe an infinite seal life from a practical standpoint anyway.
Yeah, what about the lubrication system?
Well, yeah, you know, just one other thing. Yeah, liquid cooling, okay. My system incorporates a separate electric pump that pushes coolant through the system. And the reason why it's separate, what's unique about that is we have coolant circulation even when the machine is off when required. Why is that important? Well, natural gas and other gases have a lot of moisture in there. And when you get to real cold temperatures, that freezes. And when that freezes, it can destroy a machine, it can cause failures on startup, it can introduce all kinds of problems. So what this machine does, it's never off, it goes into hibernate mode. And so let's say it's cold out, it's 0 degrees, and the competition's machine is just sitting there. The gas is freezing, the moisture in the gas is freezing inside of a valve or a piston ring, and that's not a good thing. So in our system, since we have an automatic circulating pump, that can turn on, and it does. So let's say it's at 30 degrees, it turns on, it circulates without running the machine, and it has a separate electric heater on board, which is standard equipment in this machine, by the way. And that circulates the coolant and brings it up to temperature above freezing, and then it stops the pump, stops the heater. It may even turn on the separate electric oil pump as well to warm that oil or keep it above freezing, because let's face it, you get an ice particle inside of the lubrication system, that's not good either.
Correct. And the thickness of the oil when it's very cold out.
Yeah, absolutely. Oils that are commonly used in natural gas compression machines, compressors, the oil can be thick, and obviously when it gets colder it gets thicker.
Right.
So handling problems as far as moving the oil through the system, if it's too cold, they can be a detriment to premature wear of the internal components on the machine, or even the death and destruction of the machine by simply not getting lubrication to the rings or other critical components as needed.
And how are those systems controlled?
The machine is very comprehensive, what I call sort of a nervous system, which is a bunch of pressure transducers, flow sensors. It also has incorporated a PLC and an HMI. Now PLCs and HMI in good systems is not unique, but this system being as comprehensive as it is, it even monitors the moisture inside the gas itself. And it's measuring inlet temperature, outlet temperature. So, and it's calculating the differential between those two temperatures. And with that data, which is numbers are being crunched in the machine at very high speeds, that can set off the machine to prevent itself from causing a problem by knowing that data. For instance, let's just keep it simple. Let's say the machine's in Arizona, super hot out. You're filling 10 gallons, 10 gg's of fuel in your tank, and it's 120 degrees out. The machine's running. The air-cooled machines, which is common in the industry, that thing will just keep running, even when it's hot, overheated even. And the better systems that sense that they're hot, it just alarms out and stops. Or gives you a message that it's overheating and continues to run. So our system takes action. It doesn't just say, hey, there's a problem. It sends you an email, by the way. You'll get an email and say that, system overheated. But that doesn't mean you have to go to the machine and stop it or take some sort of action. The machine takes care of itself. And how does it do that? It shuts the compression off. And so the machine stops compressing gas. The systems and subsystems are still employed. For instance, in an overheat situation, it'll stop the compression. It'll sit there and run the electric coolant pump, and it'll turn on a fan and the liquid cooled radiator, and it'll help eliminate the heat out of there. Now when the system gets down to a normal temperature, the system will then resume. It'll start the compression process once again and run. And let's say it stays hot outside, the ambient temperature is 120. And so it'll run, might overheat again. It'll stop. It won't overheat. It'll clip it, it'll stop it, it'll keep cycling on and off until its mission is complete, its filling mission of, say, 10 gg's if you program it to fill 10 gg's.
Now, you talked on the lubrication system. Tell me, what is the benefit of actually having a separate oil pump on the system controlled by its own motor?
Well, other than the fact that you heard that earlier, that when it's cold we can turn that on to keep the oil warm because it has a separate reservoir and a separate system. There's never a chance that this machine ever is going to start without having oil to full pressure. It doesn't turn 1 degree of rotation even. First thing that happens is when you start the machine, it doesn't just turn on. It prepares itself to run. And one of those preparations is it turns on the electric oil pump and pumps oil. It looks for, okay, I'm pumping oil. Am I at pressure? Yes, I'm at pressure. Then what? Then it looks for flow. Do I have flow? Because you could have pressure and no flow. You could have a bad flow switch, and so a component could be bad, a sensor could be bad. And so there's no chance that this machine is going to turn on unless it sees that the motor starter's engaged to run that electric motor that turns the electric pump. Once that's confirmed, again, we look for pressure. That's confirmed, then we look for flow. We got flow, boom. Now we can start to energize the main drive motors that run the compressor system. So there's never a chance at all that the machines running are going to even start up to get oil pressure, whereas the rest of the industry has a direct drive pump. There's nothing wrong with a direct drive pump to a crankshaft. That's how they commonly do it. But what is wrong about that, at least in my eyes, is you're getting wear during the startup procedure. So here's this thing cranking before it gets to full RPM or full pressure, and it's running literally with hoping the oil film stay stuck on there from last month. Maybe it didn't run for a month. So
Right.
we don't worry about that here, and that's why we do this.
So it establishes the flow on there so that there is no possible way that the compressor is going to start up without lubrication, proper lubrication.
No, the odds of all those system checks being all bad at the same time are nearly impossible, especially the way the ladder logic program is written, because they need to occur in certain time fields as well. So they don't not only have to be on, but they have to sustain a particular reading that's built in the system.
So what you're saying, you made a point about the startup. It sounds to me like there are several things that this machine has to go through before it'll actually start up and run.
Oh yeah, every single issue that any CNG filling station has to cope with, it's always doing system checks on a full-time basis, nearly full-time on almost all systems. So we take the oil very seriously in the cooling system, because the cooling system is the same. It needs to run, it needs to look for pressure, it needs to look for flow as well. Because if you have a problem with flow, you have a blockage, you don't have flow. If you could have pressure and not flow. So you need all these things. And the cooling system not pumping properly because of air, it's low, something. We're looking for levels in the system. Is the cooling system full? That's another thing, that it had another criteria. And if your engine on your car overheats, the engine dies. It's a certain death. Unless you stop it, it'll melt and it'll seize up, and that's the end of it. Same thing with compression systems. Absolutely the same thing. And there's no chance that there is no system or subsystem that we don't take serious and we don't measure and check on a regular basis, internally, in the machine automatically.
One thing I have heard several times is the term blowdown in compressor systems.
Yes.
Could you explain to me what that is?
Yeah. Compressor blowdown or blowdown systems are common and actually necessary, especially in explosive gas compressors, like natural gas is an explosive gas. Not that it's a bad gas, but it's something that's important. And blowdowns are used for a number of different purposes. And what that refers to normally is you're venting out pressure somewhere in the compressor system, in a line, in the compression chamber, somewhere. You're relieving that pressure. And you're doing that because, one, you have to in order to start the machine. If there's these huge pressures inside, the systems don't have enough torque normally to start. Or they could draw excessive energy to achieve a startup under that high pressure condition. And the other reason why you blow down is you want to relieve pressure, say when the system stops. You don't want these pressures sitting there because they could build up in places they don't belong, because they tend to migrate to paths of least resistance, and it could overpressurize, a gas meter. Maybe high pressure ends up in the oil system. And you want to control this, and that's what the blowdown's about. One other reason for blowdown, say during the compression process, occasionally you would blow down, is what you're doing is you're draining out non-compressibles. Oil, compressor oil. Systems that are oilless, there's still non-compressibles, as I described earlier. Propane, butane, very low pressure, gas turns into a liquid, destroys the machine. So our system is a lubricated system, and we do that to get moisture out before it gets to the next stage. We do it because we don't want it to migrate inside of filter housings and get too full and start to push a slug, so to speak, a lot of fluid into the next compression cycle. and the next stage of compression, which can cause a lot of damage. So our machine has a unique and very comprehensive blowdown system. And, you know, am I bragging about it? Yeah, because it's really unique over what the industry. You say, what are you talking about, Mike? You know, everybody talks about blowdown. They got blowdowns in there. Yeah, but not the way we do it and how we use it. In our system, it's proprietary, but it's constantly blowing down certain stages at given times, at given measurements of gas, because we have an onboard gas meter on our system. So it's not a flow meter, it's a literal gas meter, which are normally more accurate.
So you told me a little bit about the blowdown system. How does the reactor dryer system play in and work with the blowdown system, or do they?
Well, that's a good question, and the system is actually very comprehensive, and this is really what's unique, even more unique when we talk about blowdown of gases, non-compressibles, and gas contamination. So we use this system to actually help cleanse the gas, and we employ a high-pressure reactor dryer system, which I developed what I call the reactive pulse system. And what happens, this works in conjunction with the blowdown system. I know this sounds complicated, but there's a lot of tech guys out there that like to dig into things, you know, and I'll summarize this as quick as I can. But the blowdown system is helping to cleanse the gas. And in our system, we have intercooled, these are integral filters, coalescing, they are internal inside the compressor system. So they're not auxiliary systems. The reactor dryer is auxiliary, which is also integrated into our system, but it is on the outside of the machine. But so the blowdown system is working with the reactor dryer. And what happens is the machine, any compression system, no matter how it works, generates contaminants on its own. There's atoms flying off of every part that's rubbing on one another. I don't care whose machine it is or how it works. And so the compressor's producing contaminants. There's contaminants in city quality gas. Water, big problem. It's actually dangerous. Water is actually a danger besides a huge problem, which could cause intermittent hesitation in driving the vehicle. So the auto manufacturers have